This is the video solution for exam 2, and this first problem is an energy problem that is similar to a couple of problems that we did together. The first problem that we did in class, when we started the energy chapter, was we had a box at the bottom of the hill and we were pushing it up the hill, and we had to make sure that we got over the top. And the way to get over the top is you get a run at it. And in this case, I wanted you to try to make that association or try to understand that you have to get over the top of the hill. The second problem that was similar to this one was when we had a truck and a boat going downhill. That was a homework problem, and you needed to find out the stopping distance, I believe. So in this case, what I was looking for was some understanding about where the force of free body diagram, and some direction of the force of friction, that the force of friction is what moves it up the hill and what keeps it moving on the flat. So what we have is a work energy problem where this has got some work going up here. Again, force of friction has to be going in this direction, and then some work going in this direction where the force of friction is pushing it forward. In the hill, I was looking for this mg cosine theta, which is the force of friction if it's in a slip condition, and that's what it was all about. So again, I was looking for some sort of free body diagram, some sort of a direction of the force of friction. I wanted you to start with the energy relationship, and so again, I was looking for I wanted you to state the equation, make sure that we were starting with the right energy equation. T1 plus V1 plus U non is equal to T2 plus V2. And the last thing, again, is just putting all the pieces together. So again, we had some 1/2 mv squared to start. We have some friction, force times distance here. At the top of the hill, we have a 1/2 mv squared, and we have gained some mgh. So those are the pieces that I was looking for. And again, the other piece that was worth a couple of points was making sure that he got to the top of the hill. Now, those three pieces, I didn't intend to take off 6 points if you missed them all. So if you felt like I gave you penalized you too much if you missed all of those pieces but yet had substantially the rest of the problem correct, then come see me and maybe we can make some adjustments. Other than that, it was a 25-point problem, and what we were looking for was an energy approach, and when we get to the top of the hill, we should have 14.12 meters per second. This next problem is an impact problem, and I'll go through this first one first. In this case, we have a round thing, a particle coming in this way, and this guy is motionless, and then it's going to impact and bounce away. First thing I need you to do, or want you to do, is identify the line and the plane. Once you find the line and the plane, then you start analyzing the components of motion and the momentums in the line and the plane. So first thing to look at is just by observation that particle B here has no motion, has no initial motion in the plane, and therefore it will have no motion in the plane after impact either. So we know that after impact it only will have motion in the line. Because this guy is coming in this way, I think it's pretty obvious that it will only have motion in the line in this direction afterward. Particle A, however, because it's coming in, it has motion in the plane and the line, or has components of its motion in both the plane and the line. So afterward, it would generally be assumed it'll have some motion in the plane and the line. We do know that the VA plane before impact is going to be equal to the VA in the plane after impact. So the first thing I do is try do the plane first, and so I know it's VA plane 1 is equal to VA plane 2, and that is 8.66. B has no motion in the plane. Then we're going to talk about the line. We have the sum of the momentums and the coefficient of restitution. And putting those two equations together, we can find the components of VA and VB, or the components of A and B in the line, and those are VA line 2 and VB line 2. All right. So here I have the components in the plane, and here are the components in the line. And that's really the main thing. Sketching the velocity vectors on the drawing is another thing I wanted you to do. And let me just put those together. We can see that for particle A, which is right up here and right here, it has negative in the line direction, so it's going to have a negative component this way. and a positive in the plane going up this way. So the square root of the sum of the squares yields a magnitude of 8.66 with an angle of 89 degrees. VB only has motion in the line, and so it's going to go straight in this direction at 1.3 meters per second. This next impact problem is the bouncing against the wall problem. This is actually a homework problem. Well, the other one was a homework problem too. It was virtually the same thing. This one has the same picture that you had used, or that we had used in a homework problem, so I was hoping that you'd be familiar with both these things. This is almost nobody chose this problem to do for some reason. I don't know why. I think it's actually a little more straightforward. It's at least it can be pretty easy and pretty straightforward, but regardless, most of you chose the other problem. So let's talk about this one. What we've got here is the ball bouncing against the inclined wall or the angled wall, and it comes off at a speed, and the angle is given. And because the angles are given both for the approaching speed and for the exit speed, it actually makes the problem pretty straightforward. So let's talk about the plane and the line. We're going to identify the line or the plane, and the line goes up this way. And so on the plane, I know that the beginning speed is equal to the ending speed. I know that the approaching speed in the line is related to the exit speed in the line by the coefficient of restitution. So that's all I did, was just put the things in here. I didn't solve for any speeds. I didn't solve for any of the other things. I just used the ratios and the relationships here. You could have solved for speeds and you could have found the values of VA as it hits and V2 as it exits. Those are perfectly fine approaches, but in this case, all I did was talk about the plane first. I know the VA plane 1 is equal to VA plane 2, so it has the cosine of 60 component, which is going to be equal to the cosine of 45 component this way. In the line, we have the coefficient of restitution is equal to VA line 1 divided by VA line 2 divided by VA line 1. And putting those together, I get a coefficient of restitution of 0.577. All right, this next problem was a very straightforward conservation of momentum problem. And again, you had this exact problem with different values, same picture as a homework problem. So again, I was hoping that this would be quite familiar to you. So the way to set this up is that we know that the beginning momentum, because they start from rest, the beginning momentum of the system is equal to 0. Well, first of all, let's talk about the conservation of momentum. The conservation of momentum says that sum of the momentums before is equal to the sum of the momentums during the movement. And because they start with 0, I was looking for this relationship afterward. Many people gave it some initial momentum, which is an incorrect understanding of the concepts. The whole thing starts with 0 momentum if they all start from rest. If one of them had been moving, or the whole cart had been moving at the beginning of the problem, then you might have had some initial momentum. But in this case, 0 momentum to start with. So we have the VA1, MAVA plus MBVB plus MCVC. We have 3 unknowns here. We don't know what any of those actuals are, so we have to use the relative equations. I know that VA is equal to the velocity of C, which is the cart, plus the velocity of A with respect to C, which is plus 2, and then VB is VC minus 2. Plugging those in and solving, we get those answers. If you had assumed that there was a beginning momentum, then I obviously had to take off some significant points there, because that was a serious concept error. All right, this next problem is a power problem, very similar to one we did in homework, very similar to one you did in homework, where you had to come up with the speed when you at a particular spot. So let's just look at this. What I wanted you to do is start with F equals ma. This is a situation where sum of the forces is mass times acceleration. So if you look over here at the free body diagram, I have the force at the wheels. This is a friction force. This is what causes it to go forward. It causes it to go forward with some mass times acceleration. There is some drag, some force due to drag resisting that, but I put all that into the F equals ma equation and try to find the force at the wheels. Then I look at the power of the engine times the efficiency is equal, excuse me, is equal to the power of the wheels, and the power of the wheels is equal to the force of the wheels times the velocity. So this kind of extended equation is really the basis of the power equation, or the power understanding. So I put 300 horsepower times 550 foot-pounds per second per horsepower. That's our conversion factor times the efficiency, and we get the force of the wheels, which is the sum of the MA plus the required friction force right there times the velocity. And that is a solver kind of problem, because you end up having a v cubed and a v in here. It'd be pretty tough to solve that. I guess you could graph it, but I don't think anybody tried to do that on the test. This next problem is a maximum speed problem, and we did many of these in class and in homework. So again, I was hoping that you would have good familiarity with this. We didn't do this exact problem, but we did so many others that were quite similar. And what we know, or what I wanted you to take away, is that the maximum speed is found where acceleration is equal to 0. There's other methods. You can find a relationship between velocity and position if it's a position problem, or you can find a relationship between velocity and time if it was a time problem, and you could take the derivative and set it equal to 0, find some information there. But the easiest and most straightforward way is to just know that maximum speed occurs where acceleration is equal to 0. So again, F equals ma problem. So the forces I have are this tension force. It's resisted by that friction force. And when that set's equal to 0, I know that the time at which the top speed, or the maximum speed, occurs is 2.645. And I plug that into an impulse momentum equation. The reason I chose that is because this is a time-based problem. If you look at the tension here as a function of time, when things are functions of time, momentum is a better is a good way of setting this up. And so I say beginning momentum plus the integral of f dt, the forces times time, is equal to mv2. I did have some initial momentum. The forces are the pulling force minus the friction force. And many of you forgot the time on the friction force. A lot of people integrated correctly here, but forgot the time over here, so I had to take points off that. And then the ending, we have a mass times velocity, and that v2 is what we were looking for. This next problem, or set of problems, choice of problems, is we're only worth 5 points, but they're both pretty tough, and so again, I'm just trying to challenge the class a little bit with only a 5-point problem to see where we were. But this first problem was a spring problem, and we should understand that springs are best handled with energy, and what we're looking for is that the spring here is compressed, and once you let it go, it's going to have a force that's going to push the cart backward, and it's going to push the box forward. And that's what we're looking for, is what are those speeds? And we did a couple of problems like this in homework, and we did one in class that was kind of similar to this. But what I was looking for is to set this up as an energy problem, where the beginning energy was 1/2 ks squared, and after the spring expands, we would have the sum of the 1/2 mv squareds. In other words, the 1/2 mv squared of the box, 1/2 mv squared of the cart. We do have two unknowns here. We don't know the velocities at the end, so those are two unknowns, and so we need a momentum equation then, because this is also it's a conservation of energy problem, in that we're going to ignore friction during this time, so I have no work associated with this. It's also a conservation of momentum problem, because we have a beginning momentum of equal to 0, and at the end of the problem, after the spring completely expands, we have momentums of each one of those. And then we end up having two equations with two unknowns, and you sub in there, and you have to solve a quadratic, but that's not too tough on that. Anyway, you find the velocity of c, and that's what we're looking for. I think what is the final speed of the cart. All right, so I was just looking for the velocity of c was equal to 0.577 meters per second. Second question was, what's the speed of both of them together after this is all expanded? Well, again, because this was a conservation of momentum problem, beginning momentum is equal to 0. That means the ending momentum is equal to 0. After they stop sliding relative to each other because there's friction, the final speed of each of them is 0. The second one, the second choice was a homework problem. It was essentially the same thing. All I was looking for here is the angle at which the string goes slack. And what happens, if you recall, is when you slide up here, it gets to a point up here, and if you have enough speed, it'll go all the way over and keep the string tight. But if you don't have enough speed, it'll come up here and drop down. It'll become a projectile. The speed does not go to zero. What the speed does is just doesn't have enough to keep the string tight. So this is a combination of NTB and energy. And so we'll set this up first as an NTB problem. And if some of the forces in the normal is mass times acceleration normal, draw a little free body diagram over here. You got mg going down, mg cosine theta, you got the tension, and you see that the velocity is a function of theta. And then we have to do an energy problem. At the energy problem, we know it's a conservation of energy problem. I have some 1/2 mv squared. I'm going to gain some mgh, meanwhile losing some of my 1/2 mv squared. So that's what I've got here. 1/2 mv squared at the bottom. I have some 1/2 mv squared at the when it loses contact. In this case, the tension goes slack, and I've gained some mgh. The mgh is this, what we did in class, and again you did this in homework, is that the r minus r cosine theta is a good way. I think it's the best way of setting this up. That way you get a good value for h for any value of theta when it's in there. So in other words, when theta goes over 90 degrees, you're still going to get a good valid value for the height. Anyway, putting those two together, and again you've done this before, you put this in there and you can find that the theta at which it goes slack is 123.8 degrees. Well, these next two problems are concept questions. And in the first one up here, the student is throwing a ball against the wall, and she has different angles that she's throwing the ball. It all has the same speed, and they're all starting at the same height. But we did this, I did the simulation in class where we had a ball bouncing against an inclined plane at various angles of takeoff, and what we noticed that at the bottom of the hill, the speed was going to be the same under all scenarios. So that's was kind of the hint, I guess, of how to understand these things. If the coefficient of restitution, in other words, if the coefficient of restitution is equal to 1, then the bounce here loses, you lose no energy at all. So again, in that case, they all have the same speed. Now they're going to be approaching different angles when they come down, but the speed, which is the square root of the sum of the squares of the components of the velocities, the speed is going to be the same. Now the next one here is Galileo. We talked about this in class. We did a demo of Galileo. I dropped 2 balls from the second story of the engineering building. We had a video of that, and we noticed that the heavy one did fall faster. We had 2 identical balls, and the heavy one fell faster. It just did. And you did a homework problem with the terminal velocity of the skydiver. And again, you experienced that. You drew the free body diagram, and I was hoping again that you would understand that the rate of descent is dependent on the mass. In other words, if the heavier you are, all other things being equal, you will fall faster. You'll have a higher acceleration and you'll have a higher terminal velocity. Anyway, so Galileo did this from the Leaning Tower of Pisa. He said in his experiment that time of descent was not dependent on their mass. And the other way of saying it, the terminal velocity was not dependent on the mass. He would also say that the rate of acceleration was not dependent on the mass, but we know that that's not true. It is definitely not true in our experience. We did all those videos, or we did those experiments. So my point was I was hoping that you would understand that, and if you would have said no, Galileo was not correct, I would have looked at your answer a little more carefully. But this is what I really needed. I really needed a free body diagram and some explanation, some demonstration of what the terminal velocity is. That terminal velocity is higher if you have a mass, and the acceleration is actually greater if you have a mass. In this case, when you solve for the acceleration of y, the greater the mass, the bigger the smaller this term is, which means that you approach the acceleration of gravity. In this one, the bigger the mass, the higher the speed, and that's pretty obvious. Well, anyway, that's what I was looking for on these concept questions.